Okay, we are back. We're doing now page 3 of the net change packet, and I'm going to try to do this one in like short, 15 minutes or something. Let's go. This is very familiar to, this is actually in fact almost exactly like the problem on the first page. What's going on? There's water flowing into a drain pipe, and they just give you an explicit function r, and this function r represents the rate at which water flows into the drain pipe. It's flowing in at 20 sine t squared over 35 cubic feet per hour. At the same time, there's some kind of a leak, and water is draining out. And water is draining out according to this polynomial function here. Okay, so r, the rate at which water flows in, d, the rate at which water flows out, and the last very crucial piece of information that we're given is that at t equals 0, there are 30 cubic feet of water. Alright, so I can almost just do these kinds of problems in my sleep now. I know how much water there is at time 0. I have functions which tell me the rate they're flowing in and the rate we're flowing out. We're going to do integrals and we're going to figure things out. Okay, let's just do it then. Part A says, how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? So this is a pretty basic question. How much water flows in? Well, we have this function which is the rate at which water flows in, and so the whole idea of what's being tested here is, do you understand that if we take the integral from 0 to 8 of the rate at which water is flowing in, then what we get back is the total amount of water which has flowed in. Yeah, so you just integrate this using your technology, and you don't have to do anything by hand. We end up with, I'll show this calculation later, we end up with 76.570, and the units are cubic feet. They're sort of big about units. Okay, that was one part down already. Just squeeze this here, cubic feet. Okay, next, part B. Is the amount of water in the pipe increasing or decreasing at time t equals 3? Give a reason for your answer. Well, I have this function r, which tells me the rate at which water is flowing in, and so let's see what r is at time 3. And the answer is that r of 3, by just plugging 3 in, is 5.086. Units are cubic feet per hour. But what is the rate at which water is flowing out? Answer, well, that's just d of 3, and when I plug that in, I get 5.4 cubic feet per hour. And so I now reason that more water is flowing out than is flowing in. And that's all you say, right? So at time t equals 3, more water is flowing out than flowing in, flowing out than flowing in. So the amount of water is decreasing. I guess the only possible way you could get this problem wrong is if you were just really not thinking at all and you tried to take derivatives or something like that because you heard the word rate. But that's just kind of a reading comprehension thing because these functions r and d, they're already rates. Okay, so that's not even really calculus actually. This just is a problem. You could give this to a kid in middle school with a calculator. Okay, C, I think is the question, the part of this that's tricky, but only if you've never done this before. Part C says, at time t is the amount of water, at what time t is the amount of water in the pipe at a minimum? Also justify your answer. Okay, so we want to know, for the entire day from 0 to 8, when is the amount of water in the tank at a minimum? Okay, and I think what's difficult, this is exactly what I said in the video that I made earlier in the week. I think what's difficult here is that we're being asked to minimize some quantity which we don't have any sort of name for. And the quantity that we're trying to minimize is the amount of water in the tank. And so for purposes of explaining what you're doing and also helping yourself think, I think the good idea here is to pick a function and name it. So just like let f of t represent the amount of water in the tank at time t. Amount of water in the tank. Is this a tank? I guess it's a pipe. Can't keep track of what the hell is going on. It flows into a drain pipe. In the pipe, let f t represent the amount of water in the pipe at time t. Okay. Well, do I have enough information to write a formula for f? I think I do, because, and this is not our first time doing this, so I don't think I need to go slowly and explain everything, but the amount of water in the tank at any given time is going to be the amount of water that was in the tank at the beginning, which is 30, plus the change in the water in the tank. And so how fast is the water in the tank changing? Well, at any given moment, there's the rate at which the water is flowing in, which is R, and the rate at which the water is flowing out, which is D. And so if you take the difference between R and D, then that's the that's how much faster the water is flowing in versus flowing out. And so it's the rate at which the water is if this is positive, it's the rate at which water is flowing in, and if it's negative, it's the rate at which water is flowing out. It's the rate of change of the amount of water in the tank. And so we just need to, I want to integrate from 0 to t, so I'll pick a different sort of dummy variable here, just not to get that confused. Okay, so perhaps you might find it more natural to write this as two separate integrals. If I want to know the amount of water in the tank at any given moment, t, then it's how much was in there at the beginning, plus the integral from 0 to t of r would be the amount which has flowed into the pipe up to point t, and the integral from 0 to t of the d function would give the amount which has drained out up until that moment t. And so we subtract that one from that integral from this integral. So if you want to write it as two different integrals, of course it's the exact same thing, but it's really just maybe more elegant or something to think of it as just one integral. This represents the rate of change of the water, and then the integral of the rate at which the water is changing is the change up until that point t. So this is a function which takes as an input t, and which outputs the amount of water at a given moment. Okay, all of this is sort of nice because our goal now, sort of rephrased into a math problem, is to find at what time the water in the pipe is the minimum. So goal is to answer, when is F minimum? Okay, and this means that we can sort of rely on our entire sort of study of when functions have minima and maxima, and the answer is that the absolute minimum of a function on an interval is going to be at the endpoint or at a relative minimum. Okay, and so what we need to compute is, what is f of 0? Well, that I know already, it's 30. What is f of 8? That's the total amount of water in the tank at the end of the day, which I haven't calculated that yet, so I'll just do that right now. It's going to be 30 plus the integral from 0 to t, the integral from 0 to 8 of r of x minus d of x, and I don't know what that is, so I'll just leave that. I guess I have it on my paper. According to my paper, it's 48.544, and now I need to see if there are any relative minima, or places where this f function, I first need to take the derivative. So what is the derivative? Let's see, maybe I'll move over here to do this, right? So f prime of this function is And here's where you use the fundamental theorem of calculus, that the derivative of the integral is the function. F prime is, well, the derivative of 30 is 0, and the derivative of this is just going to be r of t minus d of t. This is maybe seems a little bit silly because we're just kind of going around in circles or something, because of course the rate at which the water is changing is the rate at which it's flowing in minus the rate at which it's flowing out. I sort of needed already to understand that to write that integral in the first place, but it's still nice because we have all of these theorems regarding when a function is a minimum, and one of them is that we look to see when there's a change in sign of the derivative. So since this is the derivative, I now need to look at this derivative and see when it changes sign from positive to negative. Okay, let's go. I have to move the screen around now, and I just have the previous problem still up, I think. And yeah. Okay. And I apologize again for this looking like crap, but it just does look like crap. Alright. Yeah. Alright, so once again, here we are. GeoGebra. And I guess the first thing I want to do is, yeah, I guess I need to sort of start from the beginning or something, right? So R, I think it's so great actually that we can use GeoGebra instead of our graphing calculators, because, for example, I can just name, this function sort of whatever I want, instead of having to call it like y1 or something like that, which is sort of annoying. I'll just call it R, which is what it is. And what's the other function d? It's equal to negative 0.04 t cubed t cubed plus 0.4 t squared plus 0.96t plus 0.96t. Okay, good. Oh, I think I forgot to type the equal sign, equals, and there we are. Okay, let's once again change the settings. I only want to look at this on the interval 0 to 8. And I don't know whether that's a good window. I guess it isn't, because at 8, one of them is all the way up at like 19. So let's change that to 0 to 20. So 0 to 8 and 0 to, oh man, sorry. 0. Jeez. 0. 8. 0. And 20. Okay. So that'll take a minute, but okay, there it is. Beautiful. And what else happened already sort of off screen was I took the integral from 0 to 8 of R. So let's do that now. Integral, let's try to do this correctly this time. Integral of, and I just type R. So annoying. And then you hit right arrow, I guess. Not tab. 0 and 8. Boom. And immediately we get that 76.570. That was part A. The other thing I did was just R of 3. So, boom. That was needed in part B. And D of 3 was also needed in part B. So that's just me going back and showing that. And then the other thing was, I guess I should write this f function. Can I do this even? Yeah, I guess I can. F is going to be 30 plus, I wonder if it will let me do this. I'm not even sure. Plus the integral, I bet not. Well, I don't know. Integral from 0 to, no, sorry. The integral, oh, it's not going to like this now. The integral of the r minus t function, so r of t r of t minus, I think you can maybe just type d also, and then from 0 to t. I wonder if that's allowed. No, it doesn't like that. It doesn't like that. Okay, well anyway, I don't really need this. All I need is just f of 8 at the moment. What is f of 8? It's just 30 plus the integral of, and now the function is just r minus d 0, 8. So that was just the thing, the other very last thing I did, 48.544, that's the amount of water in the pipe at the end of the day. Okay, and finally, I'm now at this moment where and it's even showing me this beautiful picture, I guess. Okay, no, this one is I guess this interval, so I don't want to look at that anymore. Okay, good, we're up to date now. What was I doing again? Oh yeah, I was trying to find the relative minimum of this f function. And I took the derivative, and the derivative was r minus d. So now the thing to do seems to be to just graph r minus d. So we graph r minus d, and do we want to call this something or don't even bother? We could call it something. We could call it, well, I'll call it f2, because what it really is the derivative of the f function. Does not like that. Okay. T equals. Okay, and that's just kind of hanging. Oh, before I look at this function, can we just say that, dude, obviously these two cross, right? And so what is the blue? The green is the rate at which water is flowing in. The blue is the rate at which water is flowing out. So first, water is flowing out more than it's flowing in. And as water is flowing out more than it's flowing in, we're losing water. And so we're losing water until suddenly we hit this point where the two curves intersect. And after that point, the green is bigger than the blue, which is to say that water is flowing in more than it's flowing out. And that means that the water in the pipe is going to be increasing. So I can just tell you right now that there's going to be a relative minimum here at this point of intersection, and that relative minimum is going to be the absolute minimum. So, okay, so I just really need to find the points of intersection of those two curves, and there are two ways to do this. You can go to Tools, Intersect, and you can just click on these two curves, and it will just construct their point of intersection A. This is kind of what we did on the previous video as well. And the answer is they intersect at 3.27 blah blah blah. And that's just going to be the answer to this problem, by the way. Another way, if it helps you to sort of think about it, is to, if you want to look at this difference function. So let's hide the original functions and let's just only look at this function f. And okay, here I'm just going to drag it because it seems easier than making a new scale. What do we see about this? What do we see? What is this? What is this function? This function in gray here? It's just r minus d. So it's the difference in the rate the water is flowing in versus flowing out. And here it's negative, and here it's positive. And so we want to know when it's 0. So we can just do this intersect thing again. I'm showing both options, and I click on the curve and the click on the x-axis and the curve. Sure. Did that actually work? No. Seemingly not. Let's try. Oh, I forgot to click intersect. X-axis, curve. Boom. B. And so what is B? It's where the r minus d function is 0. In other words, of course, it's the exact same point, because there's two different ways of thinking about the same thing. But it's the if we're thinking of this r minus d function, which on the board we called f prime, as being the derivative of f, then here we can see that the derivative of f changes sign from negative to positive at this point 3.27. Okay. So that's a critical point, and you have basically two options now. You can So the first thing I'll do is I'll compute f of this point 3.27. And how we do this is we say, oh, well, I have it up here, so that's kind of nice, right? No, well, sure. Yeah, I have this little f function right here. So that means I can, if I want to know the amount of water in the tank at this 3.27 moment, then I say 30 plus the integral from, and now here I'm going to type f2, so f underscore 2, because that's r minus d, so f underscore 2, and I want to do it at, or from rather, 0 to that point 3.27. But instead of retyping 3.27, I just say x of b. Enter. And the answer is I get 27.965. Okay, flipping this back around a minute because I think there is some discussion to be had about how best to write all of this stuff. All right, such a good video. To how best to write all of this stuff. So, okay, hopefully you followed all that. Now there are sort of two ways of kind of finishing off this problem. One way is to just say, by inspection, which is another way of saying you just did it on your calculator, man. By inspection, f prime of t equals 0 at 3.272. At t equals 3.272. That's my rounding to 3 decimal places. But you only round at the very end, not yet. Okay, so what calculus principle are you using here? You're basically saying that this is a critical point. It's a place where the derivative is 0. But notice, if you're saying that it's a place where the derivative is 0, you haven't actually argued that it is a relative minimum. But the thing is, you don't really need to argue that it's a relative minimum because we know that the absolute minimum of a function must happen at the endpoints or at a critical point. So we can just skip the step where we bother arguing that this is a relative minimum. We can just simply plug it in. And by plug it in, I mean go back over here and just compute this f of 3.272. And when you check the value of this f at one of its critical points, what you get is this number that we got, which is 27.965. Maybe I should write by inspection 0. So f has a critical number. At 3.272. Maybe that's not actually necessary. All right. So what just happened here? I was aiming to find the minimum of f. And what I did was I computed that f of 0 was 30. I computed that f of 8 was 48.544. And I computed that f of 3.272 was 27.965. And therefore, I can just conclude, so because that number is the smallest, f has a minimum at t equals 3.272. And here they're not specifically asking for what the minimum value of the water is. They just want to know at what time is there a minimum. But you sort of had to compute this number anyway because you had to compare it to the value at the endpoints to show that it was lower. Now, if you really wanted to, I'm not going to write this down, but if you really wanted to, you could answer this problem a little bit differently, which is you could say that you don't actually have to show a comparison with the endpoints. You can just know for sure that that this relative minimum will be the absolute minimum. And what you can just say, I'm not going to write this down, I'll just say it out loud, but you can just say, by inspection, f prime is negative on the interval 0, 3.272, that's true, and f prime is positive on the interval 3.2728. Therefore, the function has its absolute minimum at 3.272. which is to say, you're basically saying that not only is that a relative minimum, but it's the absolute minimum because the function is decreasing up on the entire closed interval. The function is decreasing up into that point and increasing after that point. I think that's an important observation to make, but it's sort of more work to write all that out carefully in a way that justifies it. So perhaps it's just easier to kind of mindlessly check the endpoints every time, and also just check the value for the critical numbers and just see which one is smallest. Okay, good. This is actually kind of, I don't want to say easy, but it's kind of easy. Here we go, part D. This is a strange question. The pipe can hold 50 cubic feet of water before overflowing. Oh, so this is kind of a small pipe, not a, and so if it hits 50, it's just going to overflow. For t greater than 8, okay, this is sort of new information now, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. Oh, so now they're saying continue these functions, let these two functions as presented, let them continue to be relevant, but now considering later t values. And the question is, write but do not solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Alright, well, if you've been doing this problem the way we have, this is just basically easy, right? They want to know, dude, when is the water in the tank going to equal 50? It's as simple as that. Really, they're just asking, hey, when is f of t going to equal 50? And they really want you to solve that equation. Well, what is f of t? We've already explicitly written out a formula for f of t, and if you didn't, then now's your time to do it. It's just going to be the integral from, wait a second, what's w again? Oh yeah, write but do not solve an equation about one meters that gives the time w and the pipe will begin to overflow. So f of w is, they want to know, for what time w will the pipe overflow? So basically they're just asking, dude, starting at, oh no, careful. Yeah, so basically we start at 30, and then we take the integral from 0 to w of r of t minus d of t dt, and that's it. That's just this whole problem, right? This just says that the integral from 0 to w is the change in the amount of water in the pipe. 30 is the amount of water that was there at the beginning. So the entire right-hand side of this equation is the amount of water in the pipe at time w. And all they're asking is, when is this equal to 50? And we don't even have to solve it. It just says, write but do not solve an equation, this is an equation, involving one or more integrals that gives the time w when the pipe will begin to overflow. And yeah, they just want to see if you're sophisticated enough that you sort of understand that you can have an equation and the variable can be, you know, the upper limit of integration. So they want to see, are you comfortable enough with integral functions that you are willing to write an equation that involves an integral function, and never mind how to actually solve it. Okay, that's it. That was probably like, yeah, goodbye.